Okay. Hi, everyone. My name is Shiming Zhe. I'm from Cardiff Business School. And today I'll give you a presentation about the regression. And it's nice to be here today. So today we are going to talk about 5 points. And the first point is about the simple linear regression. We will give some introduction about what the simple linear regression is and how should we interpret the simple linear regression. And the second one, we will talk about a more complex version, which is called the multiple regression. And then we will talk about the assumptions of regression analysis and how to select the best model. And the final, we will talk about the regression versus univariate methods. Which one is better, and what's the advantages and disadvantages between those methods. So let's go ahead to the part 1. It's called the simple linear regression. And we are using linear equation from our high school years. You might remember one of these equations where y is a function of x. In the statistic rule, we like to use Greek letters, and we are going to be using a slightly different notation. Our linear equation is going to have a B0 term, which we are going to be calling the intercept or the constant, and the B1, which is a term that multiplies to x, and we are going to be calling the coefficient of x or the slope of x. We call this linear equation because they will appear as a straight line if we plot them in a bidimensional plot. So we are going to talk about 2 different roles that variables play in regression models. The first one is going to be dependent variables. This is a variable that we want to explain or forecast, and we call it dependent variable because its values depend on something else. And we will be denoting it as y. And the independent variable is a variable that explains the other one. And we see that its values are independent, and we will denote this value as x when we use simple linear regression models. Now let's turn to an overview of simple linear regression. So this method is used when you want to model the linear relationship between a single quantitative variables and a single quantitative outcome variables. Although it can be also be used to estimate the relationship between a qualitative variable and a quantitative outcome. So the null hypothesis is that the B1 or the slope of the relation between x and y equals to 0. So the alternative hypothesis is that the slope does not equal to 1. If you don't understand what the hypothesis test is, we will talk this hypothesis test later. So you can see the equation down here. This is a kind of a single linear regression line. And with a single linear regression, we are using knowledge of our explanatory variables to explain or predict our outcome variable. So with simple linear regression, we fit a line to model the linear relationship between x and y. So this is the formula for the fitted regression line, as we can see that. The y hat is the predict value of y for given value of x. And in other words, it means y value for given value of x. So the predict mean value of y for given x is the sum of intercept, which is B0 plus the slopes times the given X value. And when we fit a regression line in the real world, there's always some error associated with this line. So the error is the difference between the observed y value and the predicted y value along the regression line. So as we can see, this is the observed y value. This is the predict one, observed one, predict one. So this is a error term. And the most common method to fit a regression line is the method of least squares. So this method finds the line that minimizes the variation or error around the regression line. In other words, it finds the best line that minimizes the sum of square differences between each actual observed y value and the predicted y value. So we want to minimize the error associated with our model, because the smaller the error is, the better our model will be at making predictions. So the error or the residues associated with the regression line represents what is not explained by the model. You can see that this is not explained by the model, which is the difference between the actual data points and the expect or predict data points. And I will show you an example about the linear regression. So the data I'm going to use is about the relationship between the lung capacity, age, and the height. It's this kind of data points. So I'm going to show you in the R console. So let me see. Can you see my RStudio right now?
Yes, yeah, we can see it. Thank you.
Okay, so let me show you the data first. So it's a lung capacity data, and this is the age, height, smoke, whether you are smoke or not, gender, you are male, female, and this one we just made that one. So the first thing is we're going to introduce the data and attach it. So let me plot the relationship between age and lung capacity first. We can see that this is the age, this is the lung capacity. So we may so we can begin by producing this scatter plot of the data, plotting age on the x-axis and lung capacity on the y-axis. And we may also want to go ahead and calculate the Pearson correlationship, which is 0.81, and we can see that there's a positive, fairly linear association between age and the lung capacity. And we can fit a linear regression in R using LM command. So we just call the model we fit the mod. So the lung cap is the y value and the age is our x variable. So let's put that in the commit and summarize. And this is a outcome of our mod. So we can see that it is important to know that to note that the intercept is and the age, the relationship between the intercept and the age. So the stars means whether it is a significant valuable or not. So we can see also the estimate of the intercept is standard error, as well as the test statistics and the p-value for the hypothesis test that the intercept is 0. We can also see the estimate of the slope for age is standard error, and the test statistic and the p-value for the hypothesis test. And so we can also see the R square here and the adjusted R square, as well as the coefficients and F test. And if we would like to add a regression line to this point, we can use appline command. Let me plot this. Okay, so this is the one. Yeah, so you can see that there's a line. This is a regression line, and we can also produce confidence interval for this coefficients using confit command. So here, if we would like to our confidence interval for the model coefficients, to change the level of confidence for this, we can do using level argument. So right now the confidence is 90.5%, and we can turn it to the 99%. And the ANOVA table show that the corresponds to the f-test present in the last row of the linear regression summary. So let me go back to the. So this is an example of the linear regression between the lung capacity and the age. And mostly we will fit a line through our data. And then let's talk about multiple linear regression. So multiple linear regression is just a complex version of simple linear regression. And it is used to relate two or more explanatory variables to a single quantitative outcome variable. So the regression equation is shown at the top of the slide here. And the interpretation of the intercept and the slope is similar to simple linear regression. Except that the intercept now refers to the mean value of y when all x variables equals to 0, and the slope of each explanatory variables represent the mean change in y. For which means for one unit change in x, and the y will change correspondingly. So for one unit, and we need to also remember one very important assumption, that we need to when we change in x, we need to hold in all other x variables constant. So this equation I captured is from the book. It's about the weak sales between the advertising expenditure, the price, the mentions on Twitter in previous weeks. So it shows how those variables may have relationship with weekly sales. And the x variables can be both continuous or categorical. So if your x variable is continuous, your slope tells you the mean change in y for one unit change in x, and holding all other x constant. And if your x variables is categorical, what we mean categorical is just like a male, female. Yeah, it's a kind of category things. So the slope tells us the mean difference in y between the two groups of x, holding all other variables constant. So if we want to analyze what may affect the professor's salary, so a continuous dependent variable may be just the salary, the number, and continuous independent variables are x-axis. So maybe it's the number of the courses taught and the number of publications. So maybe the more courses the professor taught, the more salary he may earn, and the more publications the more books he published, maybe he got more salaries. And categorical independent variables such as like gender and university, cities, like if a professor in London or Cardiff, etc. So, but there's a problem with categorical variables. the first thing is that the linear regression models assume that variables are numbers. So we got to have a number for those categorical variables. So what numbers should we give to different categories? And so we do this by using dummy variables. And dummy variables is a kind of binary variables, which means it takes a value of 0 or 1. We call them dummies because they are not real. They are just there to represent something else. So they are not also known as indicator variables, as they will generally have a value of 1 to indicate if an observation belongs to a category, or 0 if not. So I will show you an example of what the dummy variable is. These two graph is captured from the book. So as we can see, it is a relationship between the sales price and winter, spring, summer, fall. So if the sales is in winter, so the winter is going to be 1, and the other seasons is going to be 0. So the same. And if the variable, if the sales happens in spring, or the other variable is going to be 0, and only spring equals to 1. And it is important to know that you can see that the predictor only has winter, spring, summer. So we only need, so if we have 4 dummy variables, we only need 3 of them to generate the model, because it may lead to a collinearity. We will talk the collinearity later. So I can show you about what the dummy variable is, and by using our data. So in our data, there's 2 categories, smokers and non-smokers, and we will create a dummy variable to indicate is an observation, if an observation belongs to one of these. So if that's a smoker, so the we will give them a 1, and if that's a non-smoker, we will give them a 0. So let me show you the R script. Okay, so as we can see that we can put a class on there. So the smoke is a kind of factor. It only has no non-smokers, or yes, or a person is smokers, and we can have the level of that is no or yes. So when we generated the model LM, long capacity versus smoke, and summarize the model, we can see that it's only going to have the R console will just give us only 1 variable by default. It's because we don't need 2 variables to indicate a dummy variable. So we can. So what if we have more than maybe 2 variables, or what if we have 5 or maybe 4 categoricals? What should we do? So if we have more than 2, then just like we have 4 categories, we will use 3 dummies to represent 4 categories. Rules. So there's a rules to represent k categories. We will employ k minus 1 dummies, and then I will introduce what the multicollinearity is. So it's always occur when 2 or more explanatory variables in a multiple linear regression model are highly correlated. If two variables are collinear, you maybe want to drop one of these variables from your model. Really, this is one that you think is the least important, which will depend on your own topic area. So how to accessing collinearity? There are two methods for accessing collinearity. The first one, we just call it the correlations, is checking the correlations between all pairs of X variables. And the second one is called the variance inflation factors. It's a regression each X on the rest of other X variables. So their multicollinearity may lead to many problems, mainly concluded as three problems. So the first one, it might be lead to large errors in the estimate of coefficients of the prediction variables. And computer software is likely to be unreliable when multicollinearity is high, and different software products may estimate different models from the same data. So if you use model for extrapolation, the forecast will not be reliable. The second, which is also means the second one, the forecasting reliability. So that is, if you produce a forecast where the values of predictor variables are outside the range of values we have used to estimate the model, then the forecast is likely to have a large error. And the third one, we call it the misleading p-values. And the p-value for the coefficient in the model can be misleading. So they can suggest that we should drop the predictor variables that are in fact useful predictors. This is because the p-value tend to be too high. So as I mentioned before, if the p-value is maybe higher than 0.05, we may don't want that variables anymore. So that is, they tend not to fall below 0.05 when they should, if the multicollinearity exists. So just as I mentioned before, there are two methods to check multicollinearity. The first thing we can do is to check the correlations between all pairs of X variables. So let's just say we have 4 X variables and just call them X1, X2, X3, and X4. So you can check what is called the bivariate correlations between each pair of these X variables. For example, like X1 and X2, here we have a correlation of 0.96, which is quite high. So we are going to ask the question, how much is too much correlation? There's a general rule of thumb that say if the correlation is higher than about 0.9, this could start being a problem. But this is not a black white about it. So this is just a rule of thumb. So if you are looking for maybe when you're facing the real problem, some variables are quite important, and with also high collinearity, it might be also acceptable. So it depends on the real situation. And the second method is called the variance inflation factors. And this method is a little bit robust because unlike correlations, we are no longer looking at bivariate relationship between the X variables, and we can actually do a little bit more here. The way to calculate the variance inflation factors for each of the X variables is to create an auxiliary regression for each of the X variables. The auxiliary regression is just like the I cannot say fake regression, but it's the kind of simulate regression. So what we need to know is how much x1 is being expanded by the 3x variables. And just like this, we don't have y anymore. We put the x down there and see how x2, x3, and x4 may affect the x variables. And of course, we need to find the R square. And the R square is, if you don't know what the R square is, I have I have a slide later. So it's a kind of number that represents how your model fits your data. So as we can see, we need to find the VF using the R square from each regression. And the variance inflation factor for x1 will be 1 divided by 1 on r 1 minus r squared from this model. And this is got a subscript k here, just meaning is the r squared from the k accelerate regression. So you run this regression from regression find the r square, and you could then construct the variance inflation factor, and you would do that for the 3 other x variables as well. So this is the data. So like after we running all the x variables and put them in a dependent variable position and regress them against the 3 other x variables and see how they go with the variance inflation factors. So we can see that the x1 equals to 3.5, x2 0.4, x3 6.2, x4 10.6. So it is clear that the higher R squared, the higher the variance inflation factor will be, and we will have maybe more multicollinearity. So how high is too high for the variance inflation factors? Is there a figure beyond which we are going to say what is too high for our variance inflation factors? So there's also a rule of thumb, and typically people will say that the variance inflation factor above 10 are problematic. And the book also say that if it's over 4, we need to maybe give more attention to that variable. So in this case, if our auxiliary regression from X4 provides us with a variance inflection factor of 10.6, we need to maybe give more attention to this variable, and this maybe cause a collinearity problem. So remedies, what should we do when we face multicollinearities? So option 1 is just do nothing, because if your correlation is not super extreme, you can still just do nothing about it and be reasonably okay. And option 2 is to remove one of the correlated variables. Here you excise the actual variables and figure out whether they are providing the same information. You would want to remove one of those variables, but the problem with option 2 is that in trying to solve multicollinearity, you might actually be creating another problem, which is called the omitted variable bias. And because of all of a sudden you got a variable that is outside the model, that might be pulling the string still of the remaining variable that you are left in. So the third option would be to combine the correlated variables, just like if you have many age groups, like the 15 to 30 is the age group, 30 to 40, 40 to 60 is the age group. So you can combine like the middle age group, like the older age group. You can combine the correlated variables to see if that can make our model better. And option 4, we call the ridge and lasso regression. And this is a kind of regression that add penalty into our variables. It's a little bit complex, so we won't cover that in our presentation today. And if you are interested, you can Google that about how ridge and lasso regression works. And let's come to the part 3, which is called the assumption of the regression analysis. So there are mainly 4 assumptions: linearity, independence, normality, equivariance. And the first assumption is linearity, which means that the association between the two variables is linear, or the mean of y for given value f for given value of x is a straight line function. And independence is the second assumption, and this means that the error or residues are independent. Normality is the third assumption, and so for each value of x, the value of y are normally distributed, which also means that the error are normally distributed. And the final assumption is equivariance. This means that the error variance is constant. So the variance around the regression line is approximately the same at each point along the line. So we use diagnostic or residual plot to check the linearity and the equivariance assumption. Independence is checked through knowledge of study design, and normality is accessed by using QQ plot. So I will show you an example about how to check the linearity later. And there's also question about how do we do with the non-linearity. And as we can see that this data is clearly non-linearity, and what can we do about it? But first, we will check how to check the linearity, and I will show you my RStudio. Okay, so the mod here, we got relationship between lung capacity and age, and we can plot that mod, and we can see that this is a model plot in the RStudio, and we can see that the first things we can see that is y is the residues or errors. You can see that it's down here. And if the linearity assumption is made, we should see no patterns in here. And the red line should be fairly flat. And if the variation is constant here, we should see no pattern. This point should look like a plot of point. And when we look at second plot, and this is known as QQ plot or quantile plot. The y-axis is standardized residues. On the x-axis is ordered theoretical residues. And this is what we would expect the residues to be if the error or the residues are truly normally distributed. Right now, our model is in kind of a linear regression. So the line is the shape of line is pretty good. So so if the y value or errors on a residue terms are normally distributed, these points should fall roughly on a line like this. And the third plot here, as well as the fourth plot, you see here are other plots that can help us to identify non-linearities, non-constant variance, as well as other troublesome observations. So let me to show you what the non-linear regression looks like. So this is plot. You can see that. So this is the other plot, and you can see that there's clearly not a flat pattern and in the residues and fitted plot, and the normal QQ plot is also not a very straight line. So we can see that plot and maybe draw a conclusion that or the data that I gave in that place is not a linear regression data. So let's go back. Okay, so what can we do with those data with non-linearity? Just like I mentioned, just like I show you before, the data with non-linearity. And there are a couple of ways to do that. But today I will just introduce you just one method is to transform the variables. And you know, sometimes we need to transform the variables to make our data looks more linear. And what I mean here is what I mean here is rather than working with different type of variables, we can try to use some mathematical methods to do that. But there's also pros and cons, the advantages and disadvantages. We'll talk about it later. So today we'll just talk about one method is the log y. So we use the log function to transform the y, and it may help us to make our line more linear. So there are pros and cons about it. The first one is many different transformations available, which may lead to a linear relationship. This can help us to lead to a linear relationship, which may help us to analyze what's the relationship between our y variable and x variable. And it can also address the non-constant variance. And the cons of that is, the first is that it may lose interpretability. So this happened is especially in the effect size models. So if we are going to analyze what's the relationship between like a professor's salary and the years of he talked, so the y variable will be the professor's salary and the x will be the year he talked. If we log the y, um, and we want to analyze the effect between them, then this model will become what the relationship between the log of salary of a professor between his experience. So we cannot give a quite a good understanding of what the meaning of that what the meaning it is in that model. And also it's not able to address all non-linearities, which means it's only work for certain shapes. There are also different types of methods to transform, like we can also transform x variables, and we can categorize the x variable to achieve non-linearity. There's tons of ways, but we need to select the best one according to the real situation that we may face. And I give you an example about this is an example about the 99 species that has a brain and a body weight measurement. So as we can see here, this is the body weight of maybe a species, and this is a brain weight. And all data is just in here, and we cannot get a very clear pattern. But after we log the body weight and we log the brain weight, we can get a quite good linear pattern. And we won't. I won't talk much about the mathematic things in here. why the log x and log y can give us a better linear model. And so if you are interested about it, we can talk it about it maybe later. So how do we select the best models? The first, I need to introduce you about the concept of R square. Just as I mentioned before, some of you may not understand what the R square is. So the R square ranges from 0 to 1. So the closer it is to 1, the better our model is at making predictions. So if the R square equals to 0.5, this tells us that 75% of the variability in Y is explained by the X variables in multiple linear regression. So the R squared tell us the proportion of variation in Y that is explained by the explanatory variable in our model. And adjusted R square is adjusted for adding other variables in the model. And so when we're adding many variables, like so the adjusted R squares may be more suitable than the R squares. And it's very important to note that the R square should not be used to compare the model fits, because when we add more variables into our model, the R squares would always goes up. And we just cannot just simply judge if this model is a better model just by R square. We need to use other variables. So the next we can discuss about the partial F-test. So the partial F-test is used in model building and variable selection to help decide if a variable and term can be removed from the model without making the model significantly worse. Conversely, we can think of the test as being used to help us decide if adding a variable or a term to the model makes the model significantly better. So the partial F-test is used to compare the nested models. And the larger model, we can call it the full model, and the model with one or more variable removed, we can call it a reduced model. We can, let me give you an example about it. So if we need to build a model to estimate the mean lung capacity using age, gender, smoke, and height, the full model would be like this, the mean lung capacity and with age, gender, smoke, and height. And if we want to remove the height, we think the height is not useful to predict the lung capacity. So we can remove the height, and this model, we call it the reduced model. So the reduced model is nested within the full model. So there are two questions. Does including height in the model significantly decrease the error and significantly increase the predictive power of the model? Does the height variable significantly improve the model? So here we have two hypotheses. The original hypothesis is that the model does not significantly differ, and the alternative hypothesis is full model is significantly better than the reduced model. So let me show you an example in the R. Okay, so let me see that is in hypothesis test. Yeah, here. So the full model, as we can see, I will just name it full model, and we can summary the full model, and we can see that this is the age, gender, male, smoke, if a person is smoke, and height. And the reduced model is here. And we can summary the reduced model. And it's not the height variable is not concluded in our model. So we can compare these two models by using partial F test to see that if we can remove the height variable from our model, so we can use ANOVA. So the first variable we need to put the reduced model, and the second we need to put the full model down here. So as we can see, the model one is the lung capacity versus age, gender, smoke. Second one, lung capacity, age, gender, smoke, height. So you can see that the second model, the residue of some residual sum squares is lower than the first one, and the p-value is also less than 0.05, so we can conclude that our full model is better, and we don't need to remove the height from our original model. Yeah, the sum square error, I have mentioned that in the previous slides. Is about how close the model predicts the y value are to the observed y value. So let's go to the part 5. It's about the regression versus univariate methods. So there are 4 advantages of regression, and the book concluded as more accurate, more credible, more insightful, and more period is a more forecasting period. I concluded this for short advantages. So so the first one, more accurate, and regression models may be more accurate than the univariate models in some circumstance. But as we point out before, it's always depend on the real situation. So this will not always be the case. And so regression models can produce explanations for variance, for example, like in cells, which can lead to a more insightful forecasting. So methods like simple exponential smoothing and the Riemann models are designed for the are designed for the short-term forecasting, for example. So the simple exponential smoothing forecast for maybe more than one period ahead from a flat, maybe more than one period ahead, but regression model can use information to forecast a long way ahead. And it is also more credible because regression provides explanation for its forecast. So this may be more credible to managers than those blind explanations method like exponential smoothing, because we can see what these x variables can contribute to the y variables. Like the exponential smoothing, like this kind of method, we just cannot give a specific explanation about why we got this kind of forecasting results. But it's so it have 6 advantages. So the first one, sorry, this is disadvantages. So the data has to be collected on the predictor variable. So this may be costly and time consuming. This is the first of its disadvantages. So, and the second one, in many cases, you need to forecast the future values of the predictor variables before you can forecasting, for example, like sales. If the next month's sales depends on the weather, then you will need to forecast the weather a month ahead to produce your sales forecast. And this will compound the forecast errors and is likely to reduce the accuracy. And the third one, the regression model we have made a global model, so they are not designed to adapt to the change. So if there's any change in our model, and they are not quite can be changed very fast to adapt to those change. And there's another assumption is that all the regression model assumes linear relationship between x and y variables. So, for example, like extra dollars of expenditure on the advertising was assumed to bring the same increase in scale. But in practice, advertising expenditure may be subject to diminishing returns as it increased. So it is possible to build nonlinear relationship into regression models, and also to incorporate interactions between prediction variables, where, for example, their joint effect is greater than the sum of their individual effects. But again, this lead to more complexity in the model processing, and it is either to automate the univariate methods, and the sixth one, in some case, the theoretical assumptions underlying a regression analysis may be series validated. We have mentioned the assumptions of regressions before. So in some cases, those regression analysis may be, those assumptions may be series validated. So finally, please allow me to quote as a sentence written by George Edward Perham Box, and all models are wrong, but some are useful. Hope this presentation can help you to explain to help you to fix the problem that you may face in the real life. And if you have any questions, I'd be happy to answer that. And thank you.
Great, thank you very much, Stephen. Is there any question, Hisham, Hussein, Mingwin? If there is any question, please ask the question. I don't think there is any question. I don't see any question in the Slack as well. So I think it is fine. Let me stop the recording.